Good afternoon, everyone. Thank you all for attending the webinar. Again, my name is Philip Ransbottom, and I handle the hydroelectric industry for REXA. I'm grateful to have the opportunity to present to you this next installment of our webinar series on reliable power needle operation. We're doing something a little different this time with the webinar. For this installment, we are going to have direct insight from a customer's perspective. What better way to do that than to invite someone who has direct experience with REXA technology at his plants? We would like you all to give a warm welcome to Steve Ball, who has worked as Generation Work Management Outage Scheduler for Southern California Edison, and now Senior Project Manager for Elderidge Electric. He has a very high level of experience in the hydro industry. He joins us from Bishop, California via the teleconference, and we're very excited to have him here on the webinar. Steve, if you could, tell a little about yourself to the attendees of the webinar.
Thank you, Phil. Good morning or good afternoon, everyone, depending upon where you are in the country today. Yes, my name is Steve Ball. I kind of give you kind of a quick history. Up until, believe it or not, this last month, I was working for Southern California Edison. I enjoyed an 11-year-long career there. And then a new change came along that put me back in contact with more in the construction contracting business, which is with Elderidge Electric currently. There's lots of things on the horizon for us, and so that's what I've done. My brief history was I got started in the electrical industry a little over 25 years ago, and was in the construction industry up until 11 years ago. As I said, I worked for Southern California Edison in the hydroelectric department with a small group of generators. There was 24 small, what we call small. They were all under 30 megawatts each, the plants, but there was 24 locations. So today we'll be talking about, actually there'll be two installations I'd like to share. One of them is the primary focus, which is at Rush Creek Powerhouse out of June Lake, and then the other one is Korea number 1, which is at the Kings Canyon area outside of what we call Lemon Cove in California, a very small town. But anyway, I'm anxious to share, and we'll be picking that up soon.
Great. Thank you very much, Steve, for sharing information about yourself. We're pleased to have you here. Now, for every webinar, we continue to challenge ourselves, and we look to improve your experience when attending these events. It is important for us that the information you receive today provides you the best insight about the REXA actuators and how the technology can serve you when applied to operating the power needle. Maybe you're considering investing in the REXA technology for the next project. Maybe you're encountering issues with your current system. Whatever the reason, these webinars are here for you as a resource to learn more about REXA when it's applied to an application level for plants that have an impulse turbine. Please take advantage of using the webinar as a resource. We invite you to send us questions while the webinar is in session. Now, some attendees today may have attended previous webinars. Others may have REXA actuators installed on various applications at your plant. If you are coming from a different industry, that's okay. We're glad you are here. If you drop us a line, we can have the appropriate industry manager get in contact with you after the webinar. With that being said, welcome to the webinar, and let's begin. Okay, everyone, the agenda today is as follows. We will do a quick view of the differences between reaction and impulse turbines as a general primer, and then touch upon actuator types that include pneumatic, electromechanical, and electrohydraulic. We will talk about some of the REXA history and delve deeper into the technology. Because REXA is a type of hydraulic technology, we are going to take a closer look at hydraulic systems and compare it to the unique yet simple flow match valve system of the REXA. In this section, we will also identify what REXA is in a governor control setup and define how we provide governor control solution for your plant. Environmental regulations can be a sensitive topic to talk about. So we want to inform you and instill greater confidence that Rexicon can either reduce or even eliminate your risk. We'll show you how in the environmental section. In the final sections, we will look at some hydro installations. And Steve Ball will share his experience with Rexa actuators operating power needles at his plants. And we'll also go through as many questions as we can during the conclusion. Remember, we're going to have a contest before we answer your questions. The first person to give us the right answer for the contest will receive a prize. Thank you again, and let's begin. So, what is the difference between a reaction and impulse hydraulic turbine? Reaction turbines operate between 5 to 200 meters of head. The water under pressure traveling through the penstock is converted into mechanical energy as it passes through the submerged turbine runners. Water flow can be radial, axial, or a combination of both. Some common reaction turbines include reversible pump, Francis, mixed flow, Kaplan, propeller, and bulb. Turbine orientation may be vertical or horizontal. To control water flow to the runners, an actuator or servos are used to position wicket gates to a desired set point. Single or double actuate gate ring can position the wicket gates to regulate flow. For a double actuated gate ring, the setup is usually with two actuators operating in tandem that stroke in opposite directions to adjust the gate ring to position wicket gates. Impulse turbines are different from reaction turbines as typically they operate at much higher head ranges between 200 to 2,000 meters. Instead of having the runners submerged, the turbine is open to atmosphere. Pressurized water flowing through the system is converted into a high-velocity jet and released from the turbine nozzles that impinge on the runners of the turbine. Some turbines may have single or multiple nozzles depending on plant strategy. The power needle is positioned to regulate the flow of water from the nozzle spinning the turbine. The more attracted the power needle, the greater the flow rate. Some impulse turbines may also have a deflector that redirects water from the turbine buckets and can enhance controllability for a turbine setup. Reaction and impulse turbines have differences in operation, and geography plays a key role on turbine type. Impulse turbines are commonly used when there is limited available flow with an abundance of available head elevation. How the Rexa technology works is a critical part to understanding why the actuator provides so many advantages. To illustrate how the Rexa works and what makes it unique, we have to look at other actuator technologies. The three types we will be looking at are pneumatic, electromechanical, and hydraulic. Pneumatic actuators we will spend the least amount of time with for this webinar. Pneumatic actuators convert pressurized air to generate mechanical motion for a control process. The inherent characteristics of air, being compressible, susceptible to moisture, and sensitive to temperature change, make it less suitable for operating the power needle. Electromechanical actuators are sometimes used for operating power needles. Turbine size, duty cycle, and fail-safe capabilities can determine the use of electromechanical actuators. However, binding and mechanical components, grease fittings, and typically high voltages are some of the problems that can be encountered when using an electromechanical actuator. Using hydraulic actuation is another method to operate a power needle. Hydraulic actuation also has high performance with fast frequency response, resolution, and fail-safe capabilities. Although there are many benefits, they are not immune to the common problems associated with hydraulic systems. Failures often originate when the fluid's quality in a hydraulic system is compromised. In order to combat the effects of the hydraulic fluid breaking down, hydraulic power units, or HPUs for short, are designed around keeping the fluid clean. For systems that operate higher pressures or have air over oil systems, run an even greater risk because they are more sensitive to the changing characteristics of the hydraulic fluid. HPUs will commonly have specialized hydraulic fluid like ISO 46 and 68, multiple filters and conditioning systems, heaters and coolers, and sometimes contain more oil in order to dissipate contamination. While all of this helps with preventing hydraulic fluid contamination, inversely increases potential of environmental risk. The result of a hydraulic fluid breaking down is a reduction in performance, a potential failure, all the while adding risk to the environment. With REXA, you can avoid having to deal with trying to maintain that oil or even adding environmental risk. So if REXA is a hydraulic system, is it a hydraulic power unit? What distinguishes REXA from other technologies? What is REXA anyway? Yes, REXA is a type of hydraulic system, but is not an HPU. I'll tell you why in a moment. Now, Robert Lameau, former CEO of Mason-Neland, started REXA. He recognized the final control element of a process loop could be improved. The valve was not the culprit of many problems. It was the actuator that positioned the valve. In the 1980s, Robert Lameau, with Gary Keith, chief design engineer also from Mason-Neland, set out to develop an actuator technology, what we know today as the REXA. The patented technology known as the flow match valve, or FMV for short, inside the power module block is what gives the REXA its ability. The flow match valve enables the REXA hydraulic system to be a closed loop circuit, keeping contaminants out and oil volumes low. The REXA is a hydraulic technology, is a motor-driven device to reach target position. Once the actuator has stroked to target position, the motor shuts off and it's hydraulically locked in place. And because of the closed loop design, there are no filters or conditioning systems in a REXA. The REXA actuator is an adaptable technology, and it operates in environments that range from cold, harsh winters of Alaska to the humid, sweltering heat of the Philippines. REXA is found on numerous applications in different industries worldwide. Now, the next few slides, we're going to show an animation of the flow circuit utilizing the flow match valve. At this point, it's a slow and thoughtful explanation. And on this slide, there are areas that are labeled and will flash. The main components on this slide are the double acting cylinder, which is flashing, the series of spools and ball checks labeled FMV1 and FMV2, and at the center is the bidirectional gear pump and brushless DC motor. Now let's add some animation to the slide and look at where the oil travels. The arrow pointing right is the direction of the stroke. Follow the circle going through the circuit. Notice which port it travels through. Okay, let's switch directions. In this opposite direction, notice which ports the circle travels through. So let's look at it in a different way. In this slide, there are two pictures of flow circuits for the REXA. Each flow circuit represents the direction of the stroke. In the circled area, the spools are seated. The flow path is open, allowing oil to travel to that side of the cylinder because there is minimal resistance from the spring-loaded ball check. However, when the spool is seated, a portion of the flow path is restricted. Now look at the circled areas. Notice how the spools are engaged this time. The spool pushes up against the seated ball check while simultaneously redirecting the oil so it can be transferred to the other side of the cylinder where the spool restricts the flow is now open. In this snapshot, the actuator has reached target position. It is hydraulically locked in place. Both spools are seated and the ball checks are isolated on each side of the cylinder. With a flow match valve closed loop, you have the capabilities of 100% duty cycle for modulating control, repeatability with as much as 10 to 12 thousandths of an inch, fast frequency response, hydraulic stability, zero oil maintenance, and minimal oil, sometimes as much as 95% or more. Now, having that type of performance and capabilities are important on a number of applications. Whether you're preventing a high velocity wire draw inside a valve, trying to protect a unit during a trip scenario, or simply want to get every little amount of performance from your system, the Rexa gives you that capability. These capabilities are advantageous when operating a power needle. Now, IEEE 125 requirements for governor controls. Multiple components can be tied to a governor control setup. So it is important to identify what Rexa is for governor controls. Rexa is not a governor system, but can be tied to one. A Rexa is a type of hydraulic supply system. It is the secondary servo motor that operates the power needle for a dual regulated turbine, or the primary servo motor for a single regulated turbine. The Rexa is also the turbine control actuator that can be integrated into a governor control system. And although Rexa is not a governor, it can be adapted for multiple types of control configurations. Should the need for governor controls be required, we will work closely with the integrator to provide the right solution for the plant. The standard control configuration for the Rexa is an analog 4 to 20 milliamp signal for set point change, and it also sends a 4 to 20 milliamp feedback signal to your control system. Other optional configurations include pulse, heart, foundation field bus, and Modbus. Environmental regulations. Discussing the environment is always a hot button issue for hydroelectric plants. Preventing oil from spilling into the waterways is one that can raise concern, add pressure to operating a plant, and can endanger people and the environment. The guidelines are strict, imposing that no oil can be discharged in a waterway. How can environmental risk be reduced? What can the Rexa technology do to either reduce or eliminate a potential oil spill? There are unique advantages of using the Rexa. The closed-loop design can reduce oil volumes by as much as 95%, greatly cutting the risk of a spill. And with no requirement to maintain oil quality, there are no filters and conditioning systems that eliminate potential leak paths. Now, Rexa can be found on multiple applications throughout a hydroelectric plant. The next few slides are just some demonstrations of how the Rexa can be utilized. These units are early generation Rexa utilizing helical cylinders to operate cooling water valves. These units were installed in the early 1990s. This slide, we have a sleeve valve with fail-safe capabilities for water intake. And like the cooling water valves, this unit, sized at 2,000 pounds of linear force with a 2-inch stroke, were installed in the 90s as well. The unit in the picture operates a pilot valve to adjust the pitch of the Kaplan blades. And the Rexa operation is not limited to modulating control. Although that capability is there, it can also be used for on-off applications. In this case, it's used to operate turbine inlet bypass valves. These water storage tank controls have universal spring fail for a trip scenario. The trip function can either be clockwise or counterclockwise. This particular unit uses a double motor design, allowing for twice the speed, and if needed, redundant motor functionality for water distribution flow control. For some applications, such as cone valves, there can also be slow control for opening and closing the discharge of water. Two-speed function is available as a standard feature and can be enabled. Two-speed can be set up either for stroke direction or change the speed when a set point has been passed. We also have floodgate control. Notice next to the control enclosure is the power module, where it is located away from the area that gets flooded, giving an operator the ability to stroke the unit in an accessible, safe location. These units are on much larger sluice gates with forces that can reach 100,000 pounds of linear force with 10 feet of stroke. And because of the reliable operation of the floodgates, the customer decided to expand the use of REXA in other locations. On this slide, there are two REXA actuators operating pressure-reducing slide gates. These are high-force actuators with a 6-inch stroke, capable of generating 120,000 pounds of linear force. REXA has extensive experience on turbine control in the power industry. In this picture, the REXA operates wicket gates that use a double piston design where the cylinder moves in tandem. Cylinders in the pit are mounted via mid-pivot, and hydraulic lines are linked to the REXA skid, accessible to operators at the turbine deck. Now, a power needle is a critical application for any impulse turbine design. Power needles can operate head ranges upwards of 2,000 meters, so roughly about more than 6,000 feet. An added challenge is the ever-changing electricity demand, forcing plants to cycle more frequently. Under these conditions, REXA is well suited for reliable control of the power needle to regulate the flow of water. Now, the power needle is a great application for REXA. REXA can hold set point for long periods of time because it is hydraulically locked in place. If the set point needs to change, say for pond control or frequency recovery, the actuator can do so for a 100% duty cycle on demand. The graph on the top right of this slide shows the different set points for a given output. Notice the different increments of movement between each step change. Some of the step changes are as small as 1/4 of an inch to about 2 inches to regulate water flow.
Okay, looks like I'm going to be on deck there, Phil. Thank you very much. This is Steve Ball again. I guess we'll talk specifically about our application on an impulse hydroturbine in actually two cases, but the first one we'll focus on will be the plant at Rush Creek. To kind of give you a little bit of background, that is a power plant that is in the eastern High Sierra near the town of June Lake. Its nozzle elevation is where am I at here? Sorry, I'm going to grab my other piece of sheets here. There we go. The nozzle elevation is just over 7,200 feet above sea level, and its main reservoir is up at just over 9,000 feet. The total head, static head for that plant for both units, because it has two units in it, are 1,809 feet or 551 meters. The flow rates between the two units are a little bit different because there's a parallel set of penstocks from the upper reservoir down to the plant. When it was built in 1914, one plant was commissioned, and then 2 years later, the second unit was commissioned. And there's a little design change. So the second unit is one we're going to look at here because that's the one that was converted to use a REXA product for actuating its power needle. Unit 2 has been rated, primarily we have it rated as 6 megawatts. Has a maximum flow rate of 50 CFS at the needle. That's again a general, again full head or full reservoir and that sort of thing. So that's a maximum possible. What we were faced with back about 2007, 2008 time period, the plant itself was in a great need of an electrical upgrade as well as some structural systems and interior architectural systems and things like that. and same thing, it's adjoining a substation. Where I was involved there from the beginning was to deal with that part of the powerhouse where we changed or upgraded all its electrical systems, as well as the establishing control rooms in it, which it didn't have previously. The control systems and some of the other ancillary systems were also part of this upgrade and replacement. The turbine itself, which is on a base rating of 8,000 horsepower, was due to be replaced with a modern stainless steel turbine. And at the time, it was seen that this would be a good opportunity to look into upgrading its governing system. And now, again, where we use Alexa here wasn't specifically for governing, but it has some very key features that we added to the plant by utilizing Alexa as a needle control that gave this plant something it never historically had. If you're familiar with this type of impulse turbine, there's several different ways of regulating or governing a turbine like this. It's not really nice and slick like that six nozzle design that was shown earlier in the slideshow, which would be a vertically oriented machine. As far as shaft would be vertical and the turbine would be horizontal. The Rush Creek example is where we've got the turbine itself is in a vertical orientation, just like Phil had described earlier. The double needle, as we call it, its design. It didn't have a deflector. It didn't have a stream bender. It wasn't articulated at the nozzle body. The main power needle was done directly at the impulse turbine, and then below it there was a relief needle that was aimed at an energy absorber on the far side of the turbine pit. They were mechanically linked, so as when the turbine, let's say, was to trip, to remove water from the turbine, as the main power needle was going closed, the mechanical linkage to the auxiliary needle would pull it open to relieve or to protect the penstock from water hammer. So it would send the flow below the turbine. And there was an oiled dash pot on the end of that linkage that would have a slow rate of closure, which would take something of about 45 to 50 seconds to complete a full closure of that water. So it was a way to protect the penstock system. The problem that we had encountered historically at that plant is that it would go off grid, or the grid connection to the transmission system would be frequently interrupted through the winter months, sometimes in other months as well, either wind or some other issue. But that plant would not be able to accept load or reject load quickly enough to the satisfaction of carrying islanded load. So it was always set up to just trip on loss of system. And so the idea was to look into a way to convert that double needle to a converter, or to a deflected system, where we would put a deflector on it at its nozzle, thereby allowing the governor to control that deflector and then have some means to actuate the power needle. We had several different challenges here. However, through some analysis and what have you, there was plenty of things we had to solve it. We could have chosen a lead screw Boulevier motor system like you would have found on our other older plants, but those were single speed. And what we thought was, if we had an ability to open up the needle a little faster for frequency recovery, what we would call load acceptance, that would be more greater flexibility to the connected load. In other words, our recovery would be faster. As far as if you lose tie to the system and you have more load present in that local area than what you were running water for, that you can put more water to the turbine and have a faster recovery of frequency and of course, voltage control. We started out understanding that the penstock system was, of course, aged. It had been there from the original construction of the plant. So we had an analysis done and modeling done to determine what we would know as forces and what those acceptable limits of needle closure and needle opening would be. and how, and what we would think is a reasonable tolerance for pressure rise and pressure drop. In other words, again, still thinking of water hammer as well as any kind of pressure rise for rapid needle movement. So in that analysis, it was determined that plus or minus 10% was a reasonable area to look at. And what that gave us was this type of information here, that to close the needle, the close rate could not exceed 15 seconds per inch, which is fairly close. It's fairly slow. But then on the opening, however, it revealed that we could open the needle as fast as just under 3 seconds per inch, which again, that confirmed the idea that, wow, we could do something like frequency recovery. And how could we do that? Well, a single speed motor with a big bull gear and a lead screw wouldn't obviously satisfy that ability very easily. And it's not very concise or precise needle placement or needle positioning. We came across the Rexa product and started to evaluate its ability to do one, set points, but two, two-speed operation. So what we ultimately did was employ the Rexa servo and actuator system on the power needle, where on the close rates, the close speed was set for 15 seconds per inch and not to exceed, and that was within the design of that particular actuator, so it could not exceed that. The two-speed option is engaged only on the open. It's open call for open, and that would go up to almost 3 seconds per inch in opening. We tested this system out when it was all ready for commissioning and what have you with load banks. I think we set about 5 megawatts, 5.5 megawatts worth of resistive load out on the side of the plant, and we were able to incrementally add and subtract load. I think increments as small as 50 kW. It was originally supposed to be a graded test where we would start off with, say, half a megawatt, 750 kilowatts, somewhere in that range, and then add about a half a megawatt to it, and allow the governor to still do its job, but it would obviously not have enough water. So what that meant was a control system that recognized that, send a signal to the Rexa to begin opening the needle valve until the frequency was recovered and satisfied. However, I think a misconception from the person operating the load bank we went from half a megawatt all the way to 3.5 megawatts in one shot, and we were completely unprepared for that. However, right then and there, it took about 1 second, just over 1 second, for the turbine to actually regain control and recover frequency. That was a huge load increase, and that was one of our last test steps, but we ended up doing it right off the bat. And to say this one thing is that, say the actuator did exactly what it was supposed to do, and it opened up the needle at the 3 second per inch rate, and the recovery was just over a second, which was within our criteria of trying to get a stable frequency within 2 seconds of system disturbance. That actually worked out very, very well. Of course, there's a lot of things I guess I can go through, and I'm sure you'll have plenty of questions. The maintenance of it has been, if minimal, if that. The maintenance has been in service now for over 5-6 years, and that unit really has required almost no maintenance. The system that was there in the previous to run the power needle had about a 200-gallon oil sump tank with a what we call a low-pressure, high-volume system to operate the needle and the dash pot, which of course was also full of oil, I believe about close to 30 or 40 gallons worth. The elimination of all of that for putting the needle drive in as a Rexa, I believe we reduced that down to about 1.5 quarts. And if I'm not mistaken, the oil used in the Rexa is really not a special oil like a GST 46 or an ISO rated oil like we would use in the turbine lubrication. I think it was something like 1030 motor oil or something, but I mean, really, it's also a closed loop, so we never really have to even deal with it. And I don't recall anywhere in there about any of our maintenance issues ever being centered around that particular unit as far as the Rexa is concerned. water regulation with the power needle, because this is kind of more or less a run-of-river plant in normal operation. We match inflows with outflows up until about 2 years ago. It was very precise. We just basically would tell it where to be, or what output we wanted from the generator, or what flow we wanted through the penstock, and the control system would send the signal and it would hit it every time. So that was that, and it still stays to this day. Oh, that's a wonderful picture right there. You can see where the unit is, where it's pointed at, and where it's standing right over the main power needle body that's below the deck there. What else was I going to get to? We put another one of these together on the smaller plant on the other side of the Sierras, and its job was to modulate the power needle as well, no governing, because what it had is small unit tied to the system. It had a forebay up about 500 feet in elevation above the plant, and the idea there was to maintain a set point at the forebay level. So there was a float up there, and with a small, basically just a 4-20 system down to the plant, the REXA directly responds to that and holds set point at that forebay. So it just matches whatever inflows to outflows. Anyway, back to the Rush Creek unit here. The last 2 years, we've gone into what we call load shaping with high demand periods of the day, where we would offer more generation, and then in off-peak periods of the day, offer less generation, and allowing the upper reservoir to recover. And there's a schedule that goes involved with that that's market responsive. And the way we do that is program the control system to have set points with the plant. And as far as that kind of goes, you can kind of see the possibilities here. Again, the needle drive in this case with the REXA has been very precise and extremely reliable. The worry we had also about fail-safe, if let's just say the unit quits functioning, really is not much of a worry at all. Fail-safe in a locked position, it could run shut, it could run open, but we chose to just lock the needle in place in case the controls quit functioning or loss of signal. Anyway, there's probably plenty more you may want to ask. I will leave it at that, and let's see what questions come.
Great. Ryan, Steve, thank you both very much. Everyone that attended the webinar, I appreciate everyone being able to take that time with us today to be able to go through that. It was important for us to be able to share the experience that we have with customers out there, and something that for Steve was kind enough to volunteer his time to be able to do this. And I hope that everyone received the type of information that they were looking for in regards to understanding the technology, understanding how it operates at a site, and getting direct feedback from someone such as Steve, who's very familiar with Alexa and how he was able to adapt to his plant.